Previously, we have computed the cohomology group of the torus. Now we want to generalize that and compute the cohomology of the G-hole torus. In other words, the cohomology of a compact orientable surface of genus G. We'll denote that by sigma G. Since the G-hole torus is connected, we immediately have that H0 must be isomorphic to R. So that's done. And what remains is to calculate H1 and H2. Our strategy is going to be to use induction via the Meyer-Torus sequence. So we will take the following covering of our surface. What we do is we'll take out a torus without a point here. We let it be V, right? And then the remaining part is a G-1 whole torus without a point. We let that be U. Observe that then U intersect with V is just going to be homotopic to the circle. Now because U, V, and U intersect with V are all connected, we can start the long exact sequence at H1. So we have the following exact sequence, and we know that this is 0. Now our plan will be as follows. There are two main things that we want to show. The first thing is that this map here is gonna be 0. So that we have that this H1 here is gonna be isomorphic to this. Now the second thing we will show is that taking out a point from the G whole torus doesn't change the H1 cohomology. So this cohomology are just going to be equal, isomorphic to this H1, and thus this allows us to use induction. Alright, so let's start with proving that this map is 0. That is equivalent to showing that the map on each of these components is 0. Now, the map on each of this component is induced by the inclusion of this circle right here inside U and V. Okay, that's what we want to show is equivalent to the following. So let's say we have a G-hole torus and then we take out a point P. Let C be a circle here surrounding this P. In other words, C can be viewed as the image of some inclusion map from the circle into M minus P. And we want to show that the induced pullback map is 0. In other words, every one form omega on this M minus P, this punctured G-hole surface, it's gonna pull back to 0 on the circle C. To that end, let's recall that we have computed the first cohomology group of the circle. We show that that's isomorphic to R via the integration map. Right, so to show that this pullback is 0, we just need to check that this integral is 0. So how do we compute this integral? The idea is to use Stokes' theorem. So let's say this area here is D. Then we can view C as the boundary of this M minus D. Right, so M minus D is this part. By Stokes' theorem then, this integral of this form on the boundary is just going to be equal to the integral of d omega over this M minus D. But omega is a closed form, so d omega must be 0, so this whole integral must be 0. And so we see that the integral of this pullback over C must be 0, and thus, because this integration map is injective, in fact it's an isomorphism, we know that this pullback must be 0 in this cohomology group. So this pullback map must be the 0 map. Now observe that that pullback map is the same as this map here. Since this map is induced by the inclusion of S1, this green circle, right, into this surface minus a point. So this map here, this pullback map here is 0, and similarly, this map here on this component is also 0. So this whole map here is 0. And we have that this H1 of sigma G must be isomorphic to this direct sum. So what are these? We'll answer that in the next video. So in the next video, we're gonna compute the cohomology of the punctured G-hole torus.